A block of mass m slides down an inclined plane that makes an angle theta with the horizontal, reaching the bottom after time t. A. Neglecting the friction between the object bottom and the incline. What is acceleration of the block? What is the length of the incline? So now, what is the first step of doing this type of question? Yes, you're right. Free body diagram. Good job. So let's do it. This represents the center of mass of the object. Of course, there's gravitational force that act on the object. Since the object is on the surface that go like this, which means the normal force will always be perpendicular to the surface that it is contacting with. So the normal force will be pointing that way, around about that, Fn. So now let's break them down to the components. For this type of incline question, I will always suggest you to separate them, not using the regular x and y direction, however, using the direction that is along the incline. So the reason why the object is moving downwards is because there's a component over here that is pulling it downward, right? So the only thing we need to do over here is to find this component. And using Newton's second law, we can get the acceleration. So this is one of the components. Always remember this angle with a theta in AP1. You don't really need to worry about it right now. And yeah, this is theta, and we can get this component. Wait, this component is equal to mg times sine theta. Now let's write the net force equation for the direction along the incline, which is this direction. We can write something like net force Fx along the incline is equal to mg times sine theta, and it is equal to ma, which we can get a is equal to g sine theta. That is your answer. And second part is find the length of the incline. Also, I need to state that the block is originally at rest. So using your kinematic equation, using x is equal to v naught t plus half at squared. It's initially at rest, right? So there's no v naught t here. So there's only acceleration and t. So we can get x is equal to half times g squared times sine squared theta. Also, if you're not that good in algebra, don't write second power here because it will be theta second power, not the sine theta to the second to the squared, and times t squared. If you want, you can simplify it as half times gt sine theta squared. This looks better, and this is your answer. Now let's keep on going to the B part. With friction on the incline, coefficient of friction equal to mu1. 1. What is the acceleration on the block? 2. What is the length of the incline? So, still, draw a free body diagram. This represents the center of mass of the object. This is a gravitational force. Oh, this is a gravitational force, Fg. And also, there's definitely normal force that acts on it that is perpendicular to the surface, right? So this is a normal force, Fn. However, right now we got friction force, so we cannot neglect it. So this is your friction force, FF. Let me mention it again. When you're drawing the free body diagram, draw FF in magnitudes. When you're drawing the vector of the friction force will always be smaller than the vector of the length of the vector of the normal force. So this is your free body diagram, and now let's break them down to components along. Alright, it will look like something like that. This is your theta. So the only force that is not in components is the Fg, because other forces like Fn and Frf are all along the direction of the incline or be perpendicular to the incline. So let's break Fg to component. This is your horizontal components along the direction of incline. This is your vertical components relative to the slope. And then you can write the net force equation since the block is not moving upward or downwards vertically relative saying to the incline. We can get something like net force Y is equal to Fn minus Fg times sine theta. Wait, no, cosine theta is equal to 0. We can get Fn is equal to Fg times cosine theta. So after we find Fn, we can easily get the friction force over here, right? Since Ff is just equal to Fn times mu. So we can easily get Ff is equal to, this is supposed to be lowercase f. It's just simply equal to Fn times mu is equal to Fg times cosine theta times mu. After simplifying it, we will get mg times mu times cosine theta. I forgot there's a theta here. So this is your friction force. So now we already figured out every component along the slope direction, which means we can now write the net force equation for the direction of the incline. Net force Fy is equal to this component minus Ff. Using trig, we can get this component over here is equal to Fg equals mg times sine theta minus your Ff. I think I'll just write Ff straight down here. It is equal minus mg times mu times cosine theta equals m times a. Mu equals mu1. I forgot. So you can get a is equal to g times sine theta minus mu times cosine theta. This is a simplified version, but after you simplify the equation, it will look something like this. So don't need to worry about it, because I think it just looks better. So now we find the acceleration, right? What is the length of the incline? We're doing exactly the same thing as the last part. D is equal to V naught t plus half at squared. V naught is 0 initially, right? Because it's at rest. So it's just simply equal to half at squared. Then we just plug a over here straight down here. We can get d is equal to half times t squared times times g sine theta minus mu1 times cosine theta. And this is your answer for this part. C. The incline has a friction of coefficient of mu1. After reaching the bottom, the block continues onto a horizontal surface with a friction mu2, with the block smoothly transitioning to the horizontal surface so that its velocity at the bottom of the incline becomes the initial velocity on the horizontal surface. Find the sliding distance on the horizontal surface. So it is smoothly transitioning, right? So we don't need to worry about something like the block will be stuck at the bottom, so it will lose its velocity, yada yada yada. So we don't need to worry about it. Just remember, when the block is at the bottom, the velocity is the same. It's like this, exactly the same as the initial velocity when it start moving on a horizontal surface. So first, we need to find the final velocity after as soon as it reached the bottom of the incline. So Vf is equal to V naught t plus half at squared. The V naught is equal to 0, right? So there's no V naught here. So we can just figure out Vf by plugging acceleration to the function so that we can get Vf is equal to half g times t squared times sine theta minus mu1 cosine theta. This is the final velocity. Then it smoothly transitioned to the horizontal surface. So now let's draw a free body diagram for the object when it's moving on a horizontal surface. So this is the block, right? It represents the center of mass of the block. Of course, there's gravitational force. Now it is on the surface, so its normal force will be perpendicular to the surface, which is straight up. In this scenario, it's straight up. And since the block, after it slides down the slope, it is moving that way, right? So its friction force will be always opposing the direction it is moving, so it's going that way. This is the friction force. This is a normal force. In this scenario, since the object is always it's not moving along the vertical direction. It's not moving vertically, right? Because it's only moving horizontally. So over here, Fn is equal to Fg. Or I can write Fy is equal to 0 equals Fn minus Fg equals 0, which we can get Fn equals mg. Because Fg is equal to mg, right? And then we can get the friction force, Ff, which is equal to Fn times mu. Right here is mu mg. Mu times m times g. And now let's write a net force equation for the horizontal surface. Since it is moving horizontally and we must figure out when it stopped, right? We can find the acceleration by writing the net force equation for the horizontal direction. We can write net force Fx is only equal to Ff, which is equal to m times a2, because we cannot use a here because a we already being used. It's already being used, which we can get a2 is equal to mu2 times g, because the coefficient of friction on a horizontal surface is equal to mu2. So we will write mu2 over here. So now we figure out the acceleration. We know the initial velocity, which is over here. So we're trying to find the distance it travels, we can use a formula v squared equals v naught squared plus 2ax. Since the v, since the object come to the rest at the end, so v is equal to 0. So negative v naught squared is equal to 2ax. Now we can find x, which is equal to negative v naught squared over 2a. However, over here it's asking you the distance, which means it must be positive. And v naught squared is positive, right? And 2a, we can just plug in the magnitude, which is also positive, so that x distance is actually equal to positive 2a v naught squared. And now it's time to plug in a value. This is vf, which is equal to v naught over here, since the final velocity when the block reaches the bottom of the incline is equal to the initial velocity of the block when it starts moving along the horizontal surface. And a, which is equal to mu 2 times g, we can get x is equal to, this is a little bit complicated. A quarter of g squared times t to the fourth power times sine theta minus mu 1 cosine theta. One sec. Times 2 mu 2 times g. 1 over 2 mu 2 times g. We can cancel out one of the g. So the final answer will be, I need a ruler to draw the fraction line because it looks better. This is definitely a lot of fraction line. We'll get something like 8 mu 2 on the denominator, and on the numerator we'll get g times t to the fourth times sine theta minus mu 1 times cosine theta. And this is your answer for the last part. On the actual test, I think for AP1, your teacher will usually give you the numbers, so you really don't need to find like the expression, but I still highly recommend you to do it and to understand it because it can improve you by a lot.